I got it done really fast.
It is 9:01. I'm going to get started. Okay. Well, it's 9:01. I'm going to get started. Okay. So we will talk about the solution of this homework assignment during lab time. Okay. So when we move on to the lab, I will give you the solution to this homework assignment. And to be frank, I do not have it with me, so I'm just going to write my program during that time. And you might think that, oh, you have taught this class so many times, you must have that whole program memorized. And I can tell you that this is the second time I write it, and I definitely do not have it memorized. But I have a general idea of the strategy, and I just have to choose between a few alternatives, because I can think of a few ways to do it, and I have to kind of choose a few alternatives. And when we get to that point, that discussion, I'll let you know, what the choices might be, and the pluses and the minuses of each one. Okay. So what we'll be doing today, I think we are done with floating point number representation in this class. Yes? Okay. So what we'll do today is to move on to D flip-flop, and I wrote the note for it. I forgot to put a link into the modules so that no one actually was able to access it. But this is really kind of interesting because this is the first time we actually get to examine how does the computer remember things, okay? Because at this point we have talked about adding and subtracting, we talked about comparing, right? And pretty much, comparing comes free when you have subtraction. All you need is to throw a few more flags to it, like the sign flag, the overflow, and the L flag, and you have comparison. You have your basic less than comparison. And then we also illustrated how less than is sufficient for everything. Okay, you can use less than to implement greater than, less than or equal to, greater than or equal to, and not equal to. So we are pretty much done with calculations, okay? If anyone wants to talk about, I'm just looking at a big tree limb on that roof. From my angle, it's visible. I think it just fell maybe yesterday. I don't think the grounds people notice it because it's all kind of brown already. I don't know. Okay, I'm just hoping that it doesn't puncture anything, so that when it rains, we'll have indoor rain instead of just outdoor rain. So anyway, so we'll talk about flip-flops and latches and stuff like that today. So we'll start with the most basic item for remembering something inside the computer. All right. This is going to be a pretty long discussion, so at any time, if you have any questions, just let me know. So the first topic is an SR latch. Okay, it doesn't even look like memory to us. Okay, because you don't just say, oh, here's a 0 or 1, and go ahead and remember it. Okay, that's not how you work with an SR latch. So the first thing we want to do is to discuss, okay, what does it even look like? You can see there's no picture, okay, except a description here. So let's see if your C++, knowledge is enough to actually interpret this. Okay, so N1 and N2 are NAND 2 gates, which means they have two inputs, they're NAND gates. S and R are input pins, output pins are the Q and the NQ, and then we have 4 nodes, okay? A node is basically a connection point. It's an electrical connection point between ports, okay, points of the devices. So we are creating one connection between the input pin S and the first input of N1 as a NAND gate. We're creating another connection between the R pin, which is an input pin, and the second input of the second NAND gate. We are connecting 3 things together. So the output of the first NAND gate is connecting to the first input of the second NAND gate, but also the output pin Q.pin, and then the other one connects to NQ.pin. So this is a text description of a circuit. And you might want to say, okay, but why would we want to do something like that? Well, because if we can use text to describe a circuit, then we can use code to generate circuit. Okay? Now, this is not a hardware description language. I'm just borrowing concepts from C and C++. You can see the new node. I don't even bother to give you the class definition of node and stuff like that. But it is just understood that, okay, we're making connections between those points. So now that we have this description, let's see if we can construct the actual circuit in Logisim. So we'll go ahead and start up Logisim. There we go. So we got Logisim and we got this description. I'm going to put it side by side, like so. And the first thing we need to do is to pull 2 NAND gates. So here's 1, change the input number of inputs to 2, and make it small. Make 2 of these things. And then we have 2 input pins, 1, 2, 2 output pins, 1, 2. And I'm going to name these devices too, or name these items. This is going to be S, this is going to be R, this is going to be N1, the first NAND gate. This is going to be N2, which is the second NAND gate. And this is output Q, and this is output NQ. All right. So now we have to figure out, okay, how are we making these connections? So to do that, I'm going to move the description down a little bit like that, and then put my circuitry up. So this way we can look at the way they're supposed to be connected along with the stuff. So S as a pin, as an input pin, connects to the first input of N1. Okay, so we have a connection here. R connects to the second pin of N2. So there we go. And then we have this one is easy. So we have N1.out connecting to Q.pin, which is this one, but it also connects to N2.in. So this is the interesting part. Okay, the interesting part is not how we describe the connection of the circuitry using text, but this is the first time we see a loop. Okay, the loop is not done yet. The loop is like this. Okay, so we take the connection here, and now we have a loop, sort of a loop. Okay, but not exactly a loop. So this is the circuitry that is described by the text. So the question is, what does it do? And it does one thing that is really special. Okay, so what I will do next is I'm going to show you what it can do, and then we'll go back to try to explain how it gets it done. Okay. Okay. So we're going to change the circuitry here, bing, bing, like that. Okay. All right. So you can see this is one thing. Okay. We have S and R both inputs being 1s. Q is low or 0, and then NQ is high or 1. Okay. So take a look at this. Okay. I can do this. The inputs are still 1, 1, right? But the output has changed. And I can change it back. Okay? So in this configuration, when the inputs are both 1 and 1, the device is just maintaining its current state. When we have one of the inputs being a 0, it is changing the state to a definite state. When we have both inputs being zeros, then we are making both inputs, both outputs 1s. Is that okay so far? So now the question is, how does that work? Yep.
Is it a matter of like order or precedence in which you do the switch?
There's an order thing, but you can also see how the inputs are 1, 1s. But somehow the output is different this time. If I want to change it back to the original, this is how I change it. So you can see how the output of the first gate is becoming a part of the input of the second gate, and that the output of the second gate is also part of the input of the first gate. And they are basically negations of each other. At this point, because S and R are both 1s, so you can kind of remove those from the equation and look at N1 just as a negation gate, a NOT gate, and look at N2 as a NOT gate. But by having the output of one feeding into the other one, they are quote-unquote reinforcing the state of the entire thing as a whole. Is that okay? Any questions about this?
how are you seeing that as a NOT gate?
Okay, so when you look, this is a NAND gate. Okay, so assuming the inputs S and R are both ones, right? If one input is 1 already, then the output of a NAND gate depends only on the other gate, on the other input pin. But it's the negation of the other input pin, so that turns it into a NOT gate, into a negation. But you cannot just use 2 negations because you need something to trigger the whole thing, to set the whole thing up in the first place.
Yeah.
Okay, but functionally speaking, at this point, N1 is kind of like a NOT gate, N2 is kind of like a NOT gate. And you can just kind of imagine that S and R do not exist. Okay, but having S and R makes it possible for me to change it and go like, okay, let's change Q back to a 0. But we can maintain the state. That is the most important part. Before this, okay, with the adder and all the other circuitries that we have talked about, the input will dictate the actual output. But in this case, it is not, okay? Because 1, 1 is the same input, but we can have Q being cleared, NQ being set, or we can have Q being set and NQ being cleared, depending on what it was before this configuration of input. Is that okay so far? Does everybody understand the characteristics of this particular circuit? Not so much the explanation, but just the characteristics. S, by the way, stands for set. R stands for reset. Okay? And both of these signals are active low, which means, technically speaking, when you're looking at a real circuit diagram, a lot of times this is denoted with a /S, and this is usually denoted with a /R because it is active low. Active low means when the signal is a 0, it is active. And when it's a 1, it is inactive. When it's a 1, it says, I'm not trying to do anything. But when /S is a 0, it is trying to set the output Q to a 1. So are we okay so far with terminology? Active low, this is called an SR latch, okay? So the next thing we want to do is to analyze, okay, so how does it work? I mean, how come it has this kind of special property? Okay, the best way to look at this is to look at it in sequences. Let me set up my document camera because it's going to be helpful to describe all of that. And for those of you who are absolutely impatient and just go like, okay, I cannot wait for you to set up the document camera, you can just kind of read ahead of me because it is all explained here in text. It's just kind of tedious. So let's go back to the circuit diagram, and I'm going to set this up so that we can take a look at the whole thing. I bought the document camera for about 50, 40 bucks or so. The stand is actually more expensive than that. This extended stand thing, which allows me to okay, I need to this the right angle. There we go. I also bought this little thing here. It's just a circuit board, but it is designed to kind of plug into the USB port, and it's got an LED on it. So it is my little LED light. I think you buy like 5 of these things from eBay for, I cannot remember, like $6, $7 or something like that. If you have one of those USB charger things, okay, you can just plug in one of those things and turn your USB charger, portable charger, into a flashlight, and it will last a long time too, because I think these are fairly low current. They don't even feel warm to me. So it's really cool. Yep, that's technology. All right, so let's go to VLC.
We're recording.
Yes, we are recording, and we are capturing the audio as well. So that's a good thing to check. That's I need a way to kind of mark the angles, so that way I don't have to realign every single time. Okay, that's the focus by itself. Okay, so just need a pen right here. All right, so I'm just going to redraw the picture here quickly. Okay, so we got /s, which is set, /r, which is reset. We got two NAND gates. Okay, this is N1, this is N2. And then we got two output pins. This is Q, and this is technically /Q, which is the negation of Q, but sometimes it's not. Okay, so we just look at it as not Q. And then here we have the crisscrossing wires. Okay, so we got this output going to this. Oops, take it back. Scratch that. And then we have this output going to the other input here. There we go. Is that okay? Sorry about the confusion. That little mess here is not a connection. Okay. All right. So what we want to do is to do a analysis and say, okay, what do we know about turning the inputs to zeros? Now, because N1 is a NAND gate, so that means if at least one of the input is a 0, the output is going to be a 1. We know that for sure. Okay, we don't even care about what is /R or /Q, because as long as /S is a 0, it guarantees that Q is going to be a 1. Do we buy that? Okay. So when we analyze the circuit, we say, okay, this is /S, this is /R, and this is Q, and this is NQ. What do we know when S is a 0? Well, when /S is a 0, we know for sure that Q is going to be a 1. So now we have to say, okay, what about /R? If /R is a 1, let's make it a 0. If /R is a 0, that guarantees that NQ is also going to be a 1. Do we have any questions about the first row of this truth table? Because N1 and N2 are both NAND gates. If at least one input of a NAND gate is a 0, the output is going to be a 1. That explains the first row. Is that okay? So the second row is going to look at the situation where /S is a 0, but /R is a 1. So in that case, we know that Q is going to be a 1. That's the easy one to explain. What about NQ? Well, if Q is going to be a 1, okay, let me point out here. If Q is a 1, so that means this is a 1 coming into N2, but /R is also a 1 because that's the given value of the variable. So both inputs of N2 are 1s in this case. If both inputs of a NAND2 gate are 1s, the output is going to be a 0. So NQ in this case is going to be a 0. So are we doing okay so far with this? Okay. So the other one, the next row, is really just the symmetric opposite of what we have talked about already. So the end result is a 0 for Q and a 1 for NQ or /Q. Is that okay? So the tricky one that we need to figure out and say, okay, but how do we document this is 1, 1. Well, as it turns out, as we have demonstrated, when both inputs are 1s, the SR latch is maintaining its current state. So that means in a truth table, you just say NC for no change. Okay, it maintains whatever it was, but only if the previous state is the second row or the third row. If the previous state is the first row, then we have a kind of awkward situation. Okay, so let's go ahead and label these things. This is A0, this is A1, this is A2. I'm just giving these things specific label names. So from A1 to B, it would just do the usual thing so that we end up with Q being, okay, this is A1. So Q is 1 and Q is a 0. Okay? If we go from A2 to B, then Q is 0 and Q is 1. No big deal. So the big question is, what if we go from A0, having both inputs zeros, simultaneously changing both inputs to ones? What is going to happen? What do you guys think is going to happen?
The universe will collapse.
This is where mathematicians will have a nightmare, but not electrical engineers. Electrical engineers will look at this thing and go like, we can figure out how it works. We just need a few more parameters to figure out, the behavior of the circuit. But we'll be able to tell you what the behavior is going to be. Mathematicians, on the other hand, will look at this circuit and go like, I don't know what's going to happen. Well, because if you think about it, A0 is having both outputs being ones, right? So when you turn both inputs into ones from zeros, then N1 and N2 will simultaneously get 1, 1 as inputs, right? So both of them will try to send out 0, 0 as output. But that 0 feeds back into the input, so we have a contradiction. It seems to be a condition that cannot exist. Is that making any sense? Especially for those of you who are more mathematically inclined, right? But an electrical engineer will look at this and go like, it's not a problem because gates are not instantaneous. Okay, which means from the time a gate like N1 or N2 experiences a change in the input, it will take a certain amount of time in order for the output to change. Okay, how is that the case? Okay, so what I'm going to do now is to redraw that picture, the dreaded transistor picture that you guys really like. Like that. And then we got okay, this is important, it is not actually connecting. There we go, and then this one connects with this guy, and this one connects with that guy. Oops, there's a plate here, there you go. Do you guys vaguely remember that thing? What is that? That's our Nand gate. Very good. So now the question is, at a physical level, what is really happening when you change the input? And how come the change is not instantaneous to the output? Well, I'll just magnify a portion of this. Okay, I'm just going to magnify this portion here. And when you magnify this portion, what you will see is we have a plate here. We have some kind of insulator. And then we have the substrate of the other material. This is a P transistor, so that means the substrate is a P-type material. And then we have a plate here, and there's a little electrode here to connect to the gate. But the shaded area is an insulator. In other words, they're electrically not actually connected. Okay, this kind of transistor is called a field effect transistor because it is the electrical field that is causing the transistor to turn on or turn off. So the moment you apply or change the voltage, that is applied to this plate, you will start to have changes, over here within this region. So it will either enlarge or it will shrink in terms of, being a neutral material. When it becomes a neutral material, it is not conducting. When it becomes a P material, it is going to conduct. But that change is not instantaneous. It's not instantaneous because this is a capacitor. This portion here is a capacitor, kind of like this. In order for a capacitor to charge or to change its voltage, it needs time because there's also an inherent resistance associated with all the wiring and whatnot. So this will take time. It's a very short amount of time. We're talking about, nanoseconds here, but it will take time. Okay. So now the question is, what is going to happen when we go straight from A0 to B? Okay, and the best way to describe it is to look at the signals /S/R Q and then /Q. Okay, so we are basically saying, okay, this is 0 and we transition to 1. This is all 0. We are now transitioning this to 1, and Q used to be on the whole time. /Q used to be on the whole time because we are talking about A0. This portion is A0. Okay? So when we transition from A0 to B, what is going to happen? This is the transition right here. Okay, this transition is because of B. We're transitioning to B. Is that okay so far? So what we'll do is we're going to say, well, we'll make an assumption. Okay, it will take some amount of time for the gate to respond to the input. Okay, and we'll just say that that time is in the notes I use T1 and T2 for the two NAND gates, and we can use the same amount of time. It doesn't really matter. But I'm going to say N1 has a latency of T1, and N2 has a latency of T2, which means from the amount of time from the moment that the input of N1 changes to the time that its output changes is T1. Okay, and the same thing for T2. So that means this transition, combined with the steady state of these two, will cause the first N1 to transition after T1 amount of time. So Q is going to have a transition low like this. In other words, this is causing this to happen. And then the amount of time in between is T1. Okay? And then the same thing happens with /Q. So let's say T2 has a greater amount of time, so it takes longer because it's a slower reacting type of thing. So R transitioning is causing this to happen, but that amount of time from B is T2. Are we doing okay so far? Okay. So we still have a problem. It seems like we still have a problem because now we have both Q and /Q being zeros, which really should not be possible. But it's possible because the gates are not instantaneous. So what happens now? So what happens now is you look at this transition, and you look at this transition, and you say, okay, what is this transition going to trigger, and what is this transition going to trigger? This transition, which is Q changing, is going to trigger /Q to change, but only after a certain amount of delay. That amount of delay is, so it will take T2, okay? So it will take T2 amount of time in order for /Q to change back, because this is low and this is high. In other words, the sampling occurs at this point of time. When /R is high and Q has a transition from high to low, that is causing that transition to happen. So this transition is causing this edge to go up. What about this edge here? This edge, which is /Q going from 1 to 0, is going to cause N1 to change its output, but there's a delay associated with it, which is T1. So after T1, okay, it's getting a little bit messy here. So after T1 amount of time, from the time that /Q changes, Q itself would also make a transition back up. Is that okay? And what do we have now? Remember, /N and /R and /S are steady state, so they are constantly up. So what do we have at this point? Back to the first scenario. Okay, so this whole thing is going to repeat. This is an oscillation. Okay, it's an oscillation where the outputs, Q1 and /Q will keep going 0, 1, 0, 1, 0, 1, 0, 1 all by itself when the input stays steady as 1, 1. So this is what happens when you change /S and /R simultaneously from 0 to 1. Now if you change one at a time and the amount of time between the switches is greater than T1 plus T2, then nothing is going to happen.
What if you,
it won't get into oscillation.
In Logisim, if you use one input pin and put it to the two gate?
Logisim has the current Logisim generic, which is what I'm using right here, does not detect this kind of oscillation. The new version, the next generation, actually does detect this kind of oscillation. So that's a very good question. Go ahead.
Yeah, I was gonna say, like, how fast is that, like, oscillation?
It depends on the latency time. So the latency time, when you look at the period of this entire oscillation, it is just basically, the larger between the T1 and the T2. They can be the same. T1 and T2 can be exactly the same because, in that case, you just don't have that stagger step.
And would it just happen once, or would it happen over and over again? Would it only happen once?
It would happen over and over again, because when they get back into this state here, then we have the same situation as the original situation. So that's going to cause the next cycle to happen. And it will be the larger of the two. So T2 is basically the one determining the frequency of how frequently we go zigzag like that. Yep.
So if T1 and T2 are equal, would the oscillation still happen or not?
Yeah, it will still happen, because in that case, it's just going to be, you won't have this step here. This step here is only because T1 and T2 are different. So when T1 and T2 are the same, they both go down, then they both go up, they both go down again, they both go up again. You just won't have that staggering anymore. But it will still oscillate. So are we doing okay so far with this diagram? Okay, all right. But which also means, going from A0 to B, in one single step is not a good idea. All right, so are we okay with the concept of an SR latch? Okay, so SR latch, once again, I'm just going to recap the idea here, is, when both inputs are ones, because one is /S, which the intention is to set Q, the other one is /R, which is to reset Q, and Q is just here for the ride. Okay, for the most part, we only use one of the outputs, either Q or NQ. NQ is just, the negation of Q. But when you have, anything going low as the input, you are actuating that function. In this case, let's say we want to set Q. So by changing /S to a 0, it would change Q to a state of 1. But when you switch /S back to 1, it would just remember that state. It's not going to make any further changes. Is that okay? All right, okay. So now we make this device, and we'll go ahead and change its name. So we'll, make a component out of it first. And you can actually change the font size. So I'm going to pick a smaller font here, just so that it doesn't interfere with the rest of this design. And this is going to be /S, the set signals, /R for reset, Q, and /Q. We are building larger constructs as we go. So we got /S, Q, /R, and /Q. There we go. So now we have a component, and we want to change this name. So edit circuit layout, change the circuit name to SR Latch, and now we can create another circuit. Okay. The next circuit that we're going to create is called the D flip-flop. So we'll call this DFF for D flip-flop. So when we switch back to the nodes, we just went through all that discussion, except this is all in text, and then in the video recording you can see the pictures. So a D flip-flop looks like this. Okay, it is designed around an SR latch, but it has two additional components. So it has two additional Nand gates. It's got a negation gate, also has two input pins and two output pins. Okay. So I'm not going to read this text here. This is going to be an exercise for you to reconstruct the device. So I'm going to go straight back into Logisim and create that construct. So we'll pull a SR latch device here, and we'll just call this, okay, to be consistent here, it's called SR. And you can actually label your own component, just like that. It's pretty handy. And this is our actual negation gate. We called it N in the documentation, so I'm going to be consistent here. And then we got two NAND gates. So gates, we pull two. Are they? Oh, they're NAND gates. Okay. Just want to double check. Two inputs, narrow, like that. And then we have two of these. One is called N1, and the other one is called N2. Okay, I'm just reconstructing the circuit the way it is described. And then we got input pins and output pins. But this time the input pins are not labeled the same anymore. The first input pin, I would call the first one D for data. Okay, there we go. That's the first. The second one I'm going to call it EN for enable. And then we have the two usual output pins, just labeled Q and NQ. So this is Q, which is the non-negated output. Then this is /Q or NQ, which is the negated output. All right, so now we have to make the connections. The connections between the output pins and the output of the SR gate, latch is really just 1-to-1. Okay, so that part is fairly easy. And then the output of these two NAND gates just goes straight into the inputs, just like that. So that's pretty easy as well. The data pin, the data pin is the one that is going to have to go through the negation to go into one of the bits of N2. The enable, on the other hand, is going to go into both gates the same way. So it's just going to be like this. And this one goes to the first one. It also goes to the second one, but it goes to the second one after going through a NOT gate. I could have used a bubble here, but I did not want to because I want to illustrate the actual design itself. The reason why we have the error as the output of the SR latch is because we changed the state simultaneously from 0 to 1. So it noticed that this in simulation is going to cause problems. To fix that problem, we can just go ahead and enable. Now we have a something that's okay. So in this circuit, without describing the mechanism first, we'll just look at the behavior. Okay, how does it work? D is going to allow you to specify what are we going to store in this device. Are we storing a 0 or are we storing a 1? Okay, so D allows you to specify how you want to change the state. One single pin to control how you want to change the state of the SR latch. EN, on the other hand, is just saying, let me know when you're ready. 0 means not ready yet. 1 means I'm ready. Okay? So at this point, when EN is 0, which means I'm not ready, you can flip D any way you want and nothing changes, right? But the moment you change EN to a 1, bing, it's updated. But as long as E1 is a 1, you can change D and it will change the output. If you don't want to change the output, you have to change EN back to a 0, which disables the update of the device. Then you can change D all you want. This is why people should drive stick shift, because EN is your clutch. If you understand how to drive a stick shift, then you can say, oh, so EN is really a clutch. Right now, when EN is a 0, the clutch pedal is fully depressed, separating the transmission from the actual drivetrain, or separating the engine from the transmission. Is that okay? Are we good with this design so far? So how does it work? I mean, it seems kind of magical that we can turn an SR latch, which is kind of awkward. One pin says, if I am, activated, we'll change the output to a 1, and the other pin says, if I'm activated, we'll change the output to a 0. So we change from that to here. Well, the analysis of this circuit is actually not too bad, because when you look at EN, it goes into both NAND gates, right? When EN is a 0, like it is right now, it's guaranteeing N1 and N2 will both output 1s. Well, when N1 and N2 are both outputting 1s, feeding into /S and /R, that means you're telling the SR latch to just say, yep, keep your state, we're not changing anything. So the function of EN in this particular circuit is fairly easy to understand. Okay, when EN is a 0, no change. Now, what about D? So when you look at D, it goes into the first one. So when EN is in fact a 1, now D determines which of these two wires is going to be a 1. And the other one's guaranteed to be opposite because of the negation gate. Okay? because of this negation gate here, we guarantee that this wire between the NOT gate and N2 and this wire between N1 and D are going to be opposites of each other. Now when you have a NAND gate, and you have two NAND gates, and they have one terminal that is connected to a 1, we basically turn these two into a negation gate. And as a result, when D is 0 as it is now, the SR latch is experiencing a 0 at the /S port, and is experiencing a 0 at the /R port. But because it's active low, when the S/R is a 0, it means we want to reset the output Q from whatever it was to 0. Is that okay so far? You know how this particular gate works? Sort of. Okay. This type of D flip-flop is called level-sensitive D flip-flop. It's called level-sensitive because the current level of EN, the current steady state of EN, determines whether I can update the output or not. That's why it's called level-sensitive. So are there any questions about a level-sensitive D flip-flop? So when people just say D flip-flop, they usually refer to the level-sensitive D flip-flop. Any questions? No questions? Okay. So when I give this particular D flip-flop the name of level-sensitive, it means there's something else, right? Otherwise, we'll just call it D flip-flop. So the opposite or the contrast to level-sensitive is edge-sensitive. In other words, an edge-sensitive D flip-flop only updates the output when one of the input pins is transitioning from 0 to 1 or 1 to 0, depending on the sensitivity of the edge. Okay, so that's what we'll be talking about next. So we are done with D flip-flop, which is in section 4. The analysis of the circuit is actually pretty simple, so I don't even bother to talk about it. Section 5 talks about an edge-sensitive D flip-flop, and it's actually pretty complicated. So we'll go ahead and take a look at that design. So we'll make another design here, another circuit, and this is going to be an edge-sensitive D flip-flop. Okay. So the way it looks like is we have two SR latches. Well, there are actually 3, but I'm going to use 2 for now. So one SR latch, another SR latch here. This one, in the notes, it is called SR latch S. This is called SR latch C. C for core, and then S for setting this one here. And then we have 2 NAND gates. So we go to D NAND gates over here. But this time the NAND gates are slightly different from what we are used to, because one has 3 inputs. The other one only has 2, just like the usual ones that we deal with. There we go. And then we also have 2 input pins and 2 output pins. But I'm going to simplify to 1 single output pin, which is really just Q itself. Okay? Because NQ is really just the negation of Q. I mean, usually we only care about Q and not so much with NQ. Okay. So now we have to name these 2 NAND gates. The first one is N1. The second one is N2. Okay. And here's my data pin. And this one looks kind of different. Okay, so this is either D or data. I think I spelled the whole word in the notes, so I'm going to keep that. This one is called CLK, or the clock line. Okay, so these are all the components. And then the first thing we will do is we'll say, hey, N1 and N2, they form kind of like an SR latch. Okay, but it's not exactly like the SR latch that we have seen before. So we'll go ahead and connect things to make it a sort of SR latch. Okay. D is simple. Data just connects to one of the inputs of N2. Okay. And then we have S here, SR latch S itself, and here's the clock. So the clock line goes to both N1 and this particular SR latch. So we have one common connection between the R input and also one of the ports, I'll pick the other one, of N1. Okay? And the rest, I cannot remember. So I'm going to read this. So C.S connects to S.NQ, so S.NQ or not Q connects to C./S. So this one goes here, but it also goes to N1.in.0. So this one also goes here. And then C.R is connected from N1.out. So this one connects here. Okay. I think I'm still missing one connection here, S.S. So S.S is connected to N2.out. So N2.out, which is this wire, also goes to here. There we go. Okay. So now we have an edge-sensitive D flip-flop. So before we explain anything, this one is really hard to explain, okay? So it will take a little bit of time to explain it, but graphically it's easy to see how it works. But when you look at just the text, it takes a lot more to explain what is going on. Okay, so what we'll do is we'll go ahead and specify a transition. So the difference between this particular D flip-flop from the one that we talked about before is this one is edge sensitive. Okay, it will only sample data and update the SR latch C when clock is going from 0 to 1. When clock is 0, you can flip data all day long, nothing happens. When clock is 1, you can also flip data all day long and nothing happens. The only time that something will happen is when you have a transition of the clock line going from 0 to 1. So this is not just edge sensitive, you can also call this rising edge sensitive. Okay, so we're going to do that rising edge right now, and the output is changed to whatever the data pin is. But at this point, when the clock line is steady at 1, I can change data all day long and nothing happens. Let's go ahead and turn the clock back to 0. This time I want to update Q to a 1, so I change data from 0 to 1 first. Nothing happens. See, when clock is low, I can do this all day long, nothing happens. But when I change clock from 0 to 1, that transition updates the SR latch. So this is collectively called an edge-sensitive D flip-flop. So are we okay so far with the behavior, at least? The differences between a level-sensitive D flip-flop, which is the one before with an enable, and the edge-sensitive D flip-flop with a clock. We okay with this? Okay. And why do you think we have a clock line? And why do you think we want it to be clock or edge-sensitive instead of level-sensitive?
So that way, data changes in cycles rather than sporadically.
Right. Okay, I like the word cycles. Okay. When you buy a processor, what is one of the specifications?
Clock speed.
The clock speed. Okay. And your motherboard has its own clock speed for memory, right? And it has, so the clock, the whole idea of having a clock signal inside the computer is there. Okay, so it basically provides a time base for everything to synchronize all the things that needs to be synchronized. Is that okay? So having a particular mechanism that is edge sensitive means that, okay, there's a very specific moment in time when the output is ready to be stored that I want you to go like, now, store, okay? When you're level sensitive, during the time when the level is high, the enable is 1, there are specific times when the output of an adder is valid. That might be time when the output is invalid. So level sensitive basically means I'm going to keep the content of the last update during the time when enable is high. But that may not be, when the output of an adder or other calculation mechanism is outputting something that is valid. Is that okay? So having something that is clock edge sensitive means that you can synchronize. The first clock will clock something to the adder. The second clock will take the output of the adder and store it into something. So this way you are guaranteed that by the time you have the rising edge of the clock to store something, the output of the adder is correct already. It has settled down, it is correct. We're not going to store anything that is only intransient. Is that okay so far? Does everybody understand why edge sensitive can be important inside the processor? Okay? Very good. So this is edge sensitive. The actual mechanism of how it becomes edge sensitive is actually described here. I spent quite a bit of time to type this up. Okay, so please read it. Because I spent the time to write it. Yes?
So I just want to make sure. So this one only changes when clock goes from 0 to 1.
That is correct.
But if it goes from 1 to 0, it doesn't.
That is correct. So we can test it. Okay. Now testing it is not the same thing as explaining it. Okay. So now it has stored a 1, right? Okay. So first thing is when clock is 1, I can flip data all day long and nothing happens. Okay. The second thing we want to see is when clock goes from 1 to 0, we don't want to see a change here either, because I claim this thing is rising edge sensitive but not falling edge sensitive, and nothing happens. Okay? So the way to analyze a circuit like this is really to look at how a change or how a signal is going to cause specific components to behave. And you have to look at each and every single one and say that, okay, when this signal becomes high, it's going to happen, this is what's going to happen to this one, and so on. So the analysis is nothing more than making a fairly big table of the states of all the components here, and then just go through time and go like, okay, when this happens, that's going to happen. When this happens, that's going to happen. And you just have to track down every single one of these to figure out what is going to happen as an overall design. Is that okay? Now, when you're looking at this from the perspective of LogicSim, you can actually visualize and say, how come I can change data all day long and nothing happens? Well, you can visualize because you can see that some of these nodes never change even when I click here. You can see that only this node is updated. The rest are not. Well, why is that the case? Well, let's think about it. Data goes into just N2. Now, N2 has 2 inputs, right? One input is from the output of N1, the other input is from data. So when you change data, it does change N2 because the other one is a 1. But when N2 changes, who else is going to change at this point? Well, turns out nobody. Nobody is going to change. Why not? Well, let's look at N1. N1 is not going to change because clock is 0. So N1 has no choice but to output a 1 regardless of the other 2 input pins. Okay. Same thing with S. SR latch S also has its /R connected to clock, and clock is a 0. But the only output from S that we care about is NQ, /Q. /Q is only dependent on /R, so that's why it's guaranteed to be a 1. When the inputs to the SR latch is 1, 1, nothing happens. And that's why, once clock is a 0, you can flip this all day long and nothing happens to the SR latch. It's not ready to change state. On the other hand, when you have a rising edge right now, it is changing Q, but once you have changed, once you have the transition from 0 to 1 at the clock line, you can also see how this is not going to change a single thing. And it is kind of the same type of reasoning. When you look at N1, N1 has 3 inputs. One input is always going to be a low. So that's why the output of N1 is guaranteed to be a 1. What about the other one? What about S? When I change data, it impacts /S. of the SR latch S, right? So it will either turn it into a 0, which is going to set the SR latch C, but it's already set here. So you're not changing it. Even though you're setting it, it's already set. So when I change the data to 0, you can see how this wire is still a negative because it's maintaining the state. When I do it like this, it is still the same state because it is just either remembering the current state or it is setting. But what is setting is Q, which we don't care, we tossed it away. It's the /Q that we really care about in this case. So we still do okay so far with a edge sensitive D flip-flop. Okay. In a processor design, a lot of times we'll have devices that are configured in a multi-drop configuration, which basically means we have a whole bunch of devices listening to the same data line and the same clock line. But we don't want to update every single one at the same time. So we want to have the ability to address just one device and say, hey, you of all the devices that are also connected to the same data and the same clock line, we say, only you, I want you to update. The rest, don't pay any attention, okay? It's not your turn to update. So that means just being edge sensitive is not enough. We also want, we basically want both of those. We want it to be level sensitive with one of the pins, and we want it to be edge sensitive with another pin. In the class notes, we have that, but this time it's not in text description. This is it. So this is a gated, EN, is a gate. So it's a gated edge sensitive D flip-flop. In order for something to update, EN has to be a 1, okay? But at the same time, it won't do any updates unless clock is going from 0 to 1. So it has elements of both of those designs. It is both level sensitive as far as EN is concerned. It is edge sensitive as far as CLK, the clock line, is concerned. So you need EN to be 1 while having a rising edge transition at clock in order for data to update the SRC latch. SRC stands for, the C stands for core. Is that okay? But this is really based on the previous one, okay? Because let me change back to the previous one, and you can see how SR2 is really this thing here. Do you see this is a SR latch by itself, sort of, with the exception of N1 has 3 input pins instead of 2 input pins. But how do you make a 3 input pin NAND gate when such a device does not exist? Okay, how about this? You pull a 2 input pin NAND gate. Okay, so I'm going to change the design on the fly here. So we take one of these, and then we take a normal NAND gate. Okay, make this a small one, like so. Okay, connect the output of the AND gate into one of the inputs of the NAND gates. Do you think this as a whole is going to behave the same thing as a 3 input NAND gate? Yep, serves exactly the same thing. So that means we can replace this N1 with a construct like this. Okay, so let's go ahead and do the in place change here. So we take a look at all that, move all that stuff down. Oh, this is ugly. Okay, but it's okay, it still works. Okay, so we take out this thing, okay, and then we replace it with just a regular, okay, there's not enough space to do it. Gotta move things around a little bit. Okay, now we have space to do it. Okay, so we replace it with this. Now of the 3 inputs, 1 input can go straight in, that's fine. But the other 2 we need this construct. Okay, well, we need an AND gate. Okay, so we'll do an AND gate here. Okay, I'm missing this connection, so that should go away. And this is gonna look pretty ugly. There we go. So we got it back.
You have to move the wire on the
Huh?
AND gate.
Oh,
Your
this
clock
one?
needs to be adjusted.
Oh, this is supposed to be 2.
Just the clock.
Yep,
Did
the
you
clock
move that
needs to
down?
move down. Ding, like that. Okay, there we go. So you can see now we have a SR latch again. But this SR latch is kind of awkward because it is between N2 and N2. That's bad labeling. So we call this N1A, okay? So between N1A and N2, that's an SR latch right there. So why don't we replace this portion with an actual SR latch? So let's go ahead and take this out. Okay, this is really great. We can rip it apart again just after we make some modifications, right? So we take all of these wires out, and then we go back to SR latch, which is our own component. Okay, and then we still need this guy. This guy is still important. This goes from here. Okay, I cannot remember the actual wiring. Okay, it's okay, I can read my own description. Because N2 is basically, the output of N2 is /Q. So that goes to S.S. Okay, so S.S is this one. So this one goes to /Q. And then this one is the output of this thing. Yes, it is really, really ugly. And I think the Q is going to feed into this thing here. There we go. Okay, it just looks really ugly, okay? But functionally, I think it works. Okay, so let's try that one more time. We change the data from 1 to 0, and then we have a rising edge, updates the output just fine. And then we change the data from 0 to 1, go for another 0 to 1 transition, the output updates. So that's how it works. Okay. So from this one to both level and edge sensitive, you can see that it's pretty much the same. Except I have, instead of having the AND gate right before the lower SR latch, they only have 2 inputs. Now there's 3 inputs. Then the third input comes from enable. And then the same thing applies here. Instead of having just one single wire, which is the clock line going to the reset of SR1, now we have an AND gate to combine both the clock and the enable. So that when enable is low, it's going to force N1 to output a 0, which then will force SR1 to reset, which will force /Q of SR1 to output a 1. And at the same time, when EN is low, it would also force A2 to output a 0. When A2 outputs a 0, it's going to set the Q of SR2, so that Q, which connects to /R of SRC, would also be a 1, which means we're not making any changes to the final stage SR latch. But when EN is a 1, then it reverts back to the edge-sensitive design. It is as if it is exactly the same as the previous one. Is that okay so far? You can see how one design kind of stacks up on the next one. Okay? So we got one more thing to worry about. When you first turn on your computer, when you flip that power supply on your computer, the transistors are all over the place. Okay? They're not in a particular state. So you might need a mechanism and say that, I just need to change the output of this 1-bit memory thing to 0, regardless. Okay, I just want to reset it. That's all. But you don't want to use the clock cycle. You don't want to say, oh, but we can change it by specifying a 0 in data and specify a 1 in EN, and then have a rising edge, and that will change the output to 0. You don't want to rely on that. because it becomes chicken and egg. Because you can only control data, EN, and clock when the processor is already up and running, executing your code. But we are talking about the initialization of the processor. So we have a chicken and egg problem. We need a universal mechanism to reset the state of a D flip-flop, but without having to exercise clock, enable, or data.
Grounding.
Sort of, kind of like that. We need a reset mechanism that will be effective regardless of what the rest of these signals are doing. So that's why when we scroll down, we have the next one, which is a it looks kind of the same as the one before, right? I mean, if you compare and contrast, it looks about the same. This is a resettable, edge-sensitive, and gated D flip-flop. Okay, it's resettable because we have a reset pin. So the reset pin is the one responsible and say, do we want to change this thing to 0? Just change to 0. So when the reset pin is a 0, the reset pin, by the way, is active low, which means normally you want the reset pin to be high so that it is not resetting. But when you do want to reset the content of a D flip-flop, you want the reset pin to go low. Okay, it's active low. So let's check out how the reset pin is going to affect O1, which is an OR gate, and A3, which is an AND gate. Okay? So we first examine when reset pin is high. Okay, when reset is high, what's going to happen? When reset is high, A3 will have something and 1. What is the result of X and 1? X and true. It's just X, right? So when reset is 1, it is as if A3 is not here, and this wire just goes straight through. Q of SR2 is just connected to R of SRC when reset is high. What about O1? When reset is high, this is a negation bubble. So what is X or 0? X. Okay? So as a result, when reset is high, it is as if this OR gate is not here, and we are just connecting /Q to S of SRC. Okay? But what if reset is low? When reset is low, A3 will output a 0 regardless of the rest. And also O1 will output a 1 regardless of the rest. So you will end up with the S, which is the set signal, not doing anything. The reset signal of SRC asserted, so that SRC itself will change the output to a 0. So that's how the reset pin works. Are we doing okay so far? So now we have the ability to store one single bit. And we have many ways to control when we store that bit from data, right? Okay, so we have it's resettable, which is good, because now we can say, here's the universal reset signal for the entire motherboard. When this signal is low, everybody resets. Okay? That's what the resettable part is meaning. What the meaning of the resettable part of the name. The EN makes it gated, which means of a whole bunch of devices listening to the same data and the same clock, I can specifically say only you should update. The rest of you just ignore. Okay? And a multi-drop design is nice because it reduces routing resources. Because now you just have 2 wires going through everything, and everybody's just tapping out of it. Okay? And then the clock line makes it edge sensitive, which is great because now we can synchronize the update of these various devices so that we can say, but you update when the data is valid. At this very, very, very specific moment, update. The rest of the time, even though enable is a 1, do not do anything. Is that okay? But that's only 1 bit. How do we store a byte? What do you think? Get 8 of these things, right? So now we have this, which is called a multi-bit or 8-bit wide resettable, gated, and clock edge sensitive D flip-flop, aka a register. Yeah, we only used about an hour to talk about it. To went from the SR latch, which we built out of Nand gates, into a register, a single 8-bit register. So the next question is, so do we have to build these parts into our own library and then use these, well, you can, but you don't have to. Because when you go to LogicSim and you go to memory, and one of those things is a register. So when you hover over these various connections, or better yet, okay, this is a good time to remind you guys how to use LogicSim. Go to help. LogicSim has a very good and extensive help. When you go to library reference and go to memory library and go click on register, it will talk about the registers, all the various pins of the register. And it will talk about the east edge labeled Q, which is the output. Okay, that's our Q. West edge labeled D, which is the input. West edge labeled EN is enabled. When this is 0, clock triggers are ignored. The current value continues to appear on the output when the clock triggers are enabled. When this input is the clock triggers are enabled when this input is 1 or undefined. Okay, so that's exactly the same thing as our EN with our design. Clock input is south edge. At the instant that this input value rises from 0 to 1, a rising edge, the register's value will be updated to the value of the D input. Well, isn't that the same thing as our CLK? All right. South edge labeled 0, asynchronous reset. When 0 or undefined, this input has no effect. This is the only difference, is the way they implement the reset is it is active high, but the way that I implement it is active low. Okay, but that is easy to flip because you just have to change the bubble. Okay, move the bubble, move the gates. Okay, change the gates from the OR gate and the AND gate. They have to flip. That's the only thing you have to do. All right, so we have registers, we have an adder, we have a subtractor so far. So do we have a processor yet? No, but we have some major parts of a processor. Because what do you think a processor does? It does processing, okay? So what is processing? What does it involve?
I think it's computing, right?
Computing. So tell me what usual things you want a computer to compute. Adding, subtracting, multiplication, and division. Okay, very good. So with multiplication and division, you also need a bit shift operation, especially for division. Shifting is going to be really useful. So we need a shifter, but shifters are pretty easy to implement because all you have to do is to say, okay, the next update, you get his input, you get his input, you get his input, and then update, right? So that's not really difficult to express. It's not like an adder where you have to deal with all the carry, look ahead, and whatnot. Okay, so what else do you think a processor does? Okay, if a processor only performs computation, okay, it's kind of boring. It's kind of like having a C program that only has assignment statements and no ternary operator. Okay, so what else can a program do in C and C++? Other than assignment statements, which performs all the computation, right? You got loops and conditional statements, right? And what do you think they correspond to when you're looking at it from the perspective of the processor? It has a way to choose, right? It is the ability to choose and the ability to say, depending on something, sometimes I want to continue execution with the next location, and other times, I want to go somewhere else to continue execution. That's the basis of decision making from the perspective of the processor. Okay. We got 5 minutes left. I'm aware of the time, and you can see this entire module in Canvas is called the von Neumann Architecture in memory. So the question is, who is this guy? Who's this dude called von Neumann? And what is his contribution? What is his contribution to computers? What do you think? Does anyone know the history of von Neumann? Okay, everybody knows about Alan Turing because of the movie, but there's no movie yet made about von Neumann. And von Neumann is actually, if not as important, he might be more important to humanity compared to Alan Turing. Because von Neumann is not just a computer scientist. He's not just a mathematician. He's also an expert in statistics, electrical engineering, physics, and so on and so forth. And he's good at every single thing. Okay, if you ask a mathematician about von Neumann, a famous mathematician, I'm not talking about just a normal mathematician, the famous mathematician will say, oh, von Neumann is a genius. If you ask a famous physicist, the famous physicist will say, oh, von Neumann is an exceptional, bright, brilliant physicist. If you ask a computer scientist, famous one, the famous computer scientist will say von Neumann is an exceptionally brilliant computer scientist. He is good at just about everything. He is also very good at annoying Albert Einstein, because they were both at Princeton at one time. They were both professors at Princeton, and they share the same hallway. Albert Einstein prefers to work quietly. This guy likes polka music. Of all kinds of music, he likes polka. Okay? So it is not uncommon that this guy would be playing loud polka music from his office, and then down a few rooms, is Albert Einstein trying to work on his stuff. This guy died early. I think he died in his 50s, which is really, really early. No, he was not poisoned or assassinated, or committed suicide like Alan Turing, depending on which theory you subscribe to. He died from cancer. He died from cancer, and many people believe that he died from cancer because of his participation in the creation of not the atom bomb, it is the hydrogen bomb. So he was actively involved in the creation of the hydrogen bomb as well. Okay, we got 2 minutes left. If it is not for this guy, you wouldn't be able to update your apps. Okay? Because it is, before him, computers can be reprogrammed. But reprogramming a computer involves turning it off, opening the back, look at all the gazillion wirings, and change the wirings one at a time. You're literally changing how things connect physically in order to quote-unquote reprogram a computer. Now, back in those days, computers are fairly simple, okay? But it will still take days, even an entire week, in order to update a complicated program. Think about your apps now. Your 20 megabyte, tiny little Android app. Think about how much time it will take to rewire physically to change the behavior of the program. He's the first guy who thought of, hey, we got data already stored in memory, and they can change in time, right? And then we can retrieve memory. We can retrieve content from memory anytime we want to. And he's the first one who said, why don't we store instructions in memory too? Why are we having these instructions or the behavior of the program specified by wiring when we have RAM to store the data? So he is the guy who thought of using memory to store the instruction of a program instead of hardwiring the behavior of a program into a computer. So without him, you guys will be rewiring all day long when you need to update something on your phone. And of course, those wirings will be very small, and you'll need microscopes to do all the rewiring. So his contribution to computers is tremendous. Okay, it doesn't feel like it's really a lot, but from the practical standpoint, he is, his contribution is major. Alan Turing has contributions in the theoretical department. This guy has contribution in the pragmatic department. Okay, so we are running out of time today. You know, when we go to the lab, I'll work on the homework assignment that was due about an hour and 20 minutes ago. So that's what we'll do in the lab. I will have more notes ready by next week, but on Thursday, I'm going to give you guys a practice exam. So the next Thursday will be the first exam 1. Okay, so exam 1 will cover double representation. Yep.
So you can make any new assignments or no?
I'm going to make a new homework assignment because I think that's one way to study for the exam.
But it's not being assigned today?
Huh?
It's not assigned today? It's
It will be assigned later today, you know, and we can fudge with the due date a little bit.
Okay.
Yep. All right, so I'm going to meet you guys over at the lab.